Hey everyone, and welcome to today's explainer. I am absolutely thrilled to have you here because today we're going to decode a manufacturing challenge that honestly, on the surface, sounds physically impossible. If you're a focused learner who loves breaking down highly complex mechanical concepts into clear, logical steps, well, you are in the exact right place. We're going to unpack the seemingly magical world of polygon milling and turning. Let's get right into it.
Okay, think about this for just a second. How do you cut a perfectly flat square, or maybe a hexagon, onto a cylinder without ever stopping that cylinder from spinning? Normally, right, in a traditional machining setup, if you want a flat surface, you stop the lathe spindle, you lock it down, and you bring in a milling cutter. But what if stopping costs too much time? What if it totally ruins your process reliability? Well, today's explainer is all about this mind-bending paradox of cutting straight lines on a spinning lathe in continuous motion.
Okay, let's dive into this. Here is our roadmap for today. First, we'll hit the spinning flat paradox. Second, the spirograph principle. Third, turning versus milling. And finally, we'll wrap up with a real-world machining success story.
Starting right off with Section 1, the spinning flat paradox.
Now, what's really interesting about this slide is the tooling itself. To understand how we create flat geometry on a rotating workpiece, you really have to look at these WEP cutter heads from Schwanog. They are specifically designed for polygon turning. Just notice that aggressive multi-tooth layout. These inserts aren't your everyday lathe tools. Polygon milling and turning let us machine flats on rotationally symmetrical parts using CNC lathes, Swiss-style lathes, you name it, even multi-spindle machines. And the actual number of flats on your final part? That depends entirely on the number of teeth on this specific cutter, combined with the transmission ratio between the spindle and the tool.
The core concept here, the whole secret sauce, is synchronization. Instead of the traditional method where we have to slam the brakes on the spindle to mill a flat, which is essentially an interrupted process, polygon turning keeps both the workpiece and the tool spinning. They run at a tightly synchronized transmission ratio, usually in an up-milling direction, and because they literally never stop moving, the cuts are perfectly continuous. The process essentially superimposes two circular movements over one another. Now, technically, yes, this does lead to very slightly convex or concave surfaces, but honestly, this effect is microscopic, insignificant for most applications, and you can minimize it even further just by using proportionally larger cutting diameters.
Moving right along to Section 2, the spirograph principle.
So, the mathematical secret making all of this possible is a shape called the hypertrochoid. These are roulettes created when a circle rolls around an inner circle. If you're creating a 3, 4, or 5-sided polygon, they are formally known as H3, H4, or H5 profiles. In fact, this type of polygonal shaft and collar connection is so incredibly robust that it was officially standardized in November 2021 under DIN 3689-1. But hey, if hypertrochoid sounds way too academic, just think back to when you were a kid. Remember the flower-like patterns you made when drawing with a spirograph toy? Yep, those are hypertrochoids. Polygon turning is literally just industrial-scale spirograph math.
Let's move to and see how this builds into mechanical steps on the actual machine. Step 1, the tool and the workpiece rotate in the exact same direction, so say both are going clockwise. Step 2, their axes are not perfectly aligned. They're actually offset from each other by a specific distance or eccentricity. And Step 3, the tool rotates faster than the workpiece at a strict synchronized transmission ratio. It's this very specific combination of same direction spin, axis offset, and synchronized speed that just magically shears a flat plane right onto that round stock.
And here is the golden rule for most flat-sided polygons, a 2-to-1 ratio. The cutter head generally rotates at exactly twice the speed of the part. Because of this 2-to-1 ratio, each cutting edge on the tool turns a pair of opposite flats on the part. So if you take a cutter with 3 inserts, kind of like the one we saw earlier, and you spin it twice as fast as your workpiece, boom, you produce 6 flats, a perfect hexagon. The number of flats produced is always exactly twice the amount of the cutting edges when you're using this ratio.
All right, Section 3, turning versus milling. Let's stack them up against each other.
So the crucial point is the sheer difference in efficiency. Look on the right at traditional milling. It's an interrupted process. You have to stop the main spindle, engage your live tooling, make your cut, index the part. It's a whole ordeal. It results in way slower cycle times. And critically, if you are using a small tool on really hard material, that tool is highly prone to bending or deflecting under all that cutting pressure. But on the left, look at polygon turning. It's a continuous, unstoppable cut with synced axes. The tools used here are almost as large as the inner polygon itself, which makes them incredibly stable. There is virtually zero tool deflection, and it is dramatically quicker than milling.
In real time, it looks exactly like this. The tool and the part are just rotating together harmoniously. The tool begins a radial plunging procedure engaging the material. And because of that synchronized 2-to-1 speed and those specific tooling inserts, the tool just feeds straight in and disengages, leaving behind these perfectly machined flats. The radial plunging procedure even lets you machine flats behind a collar on the part. You can also use longitudinal or axial turning to create super long flats right along the length of a shaft. The whole shebang happens in one fluid, continuous motion.
Finally, let's hit Section 4, Real-World Machining Success. Theory and cool animations are great, but let's look at a practical reality from the tooling manufacturer, Horn. As Dollhouse explains here, they had a massive headache out on the shop floor. Their customer needed an internal polygon with 3 corners, produced on a multi-spindle automatic lathe. The material, 42CR-MO4, which is a really tough, high-strength steel. The main problem was the tiny diameter-to-length ratio of the tool they had to use. Originally, they planned to just mill it, but the milling cutter simply deflected under the immense force. That meant they would have needed an entirely separate finishing process just to fix the dimensional errors, and they absolutely didn't have the time for that in their production cycle.
So, what did they do? The solution was switching to synchronized polygon turning. They pre-bored the component, synced up the tool and component rotations, and fed the tool strictly in the Z-axis. And you guys, the results were staggering. The tool was so stable it achieved the full depth of cut in just one single pass. They completely eliminated both the milling process and the finishing process. This saved a massive 10 seconds per cycle, which, if you know high-volume manufacturing, you know that is literally an absolute eternity. Tool deflection was gone completely, and their overall process reliability just skyrocketed. Needless to say, the customer was pretty thrilled.
We've seen how overlapping circles can shear perfectly flat lines, turning a huge interrupted milling headache into a continuous, high-speed turning success. But I really want to leave you with this one thought. If manipulating synchronized circular motion can create perfect hexagons and squares in the blink of an eye, what other seemingly impossible geometries are just waiting out there to be unlocked by advanced kinematics? The capabilities of modern machining go so far beyond just straight lines and simple spins. Thank you so much for joining me for this explainer. Keep analyzing, keep learning, and I will see you in the next one.